Hello everybody. So we are back with the next video from the foundation series. And today's topic of interest is going to be electronic configuration. Electronic configuration. Okay. So just a quick revision on what was dealt in the previous session. So we discussed what principal quantum number is. Yes, we did discuss that principal quantum number gives an idea about the shell of the electron. The electron occupies certain positions, and those positions are called the shells. And the value of the principal quantum number gives an idea about that position. If the principal quantum number is known, we can get idea about the energy of the electron. We can get idea about the velocity of the electron, and also we can get an idea about the radius of that particular shell. All these were discussed in the previous session, right? And then we said that there is another quantum number which is named azimuthal quantum number, notated by L, and that represents the number of subshells. It represents the number of subshells in it. So if you can see n is equal to 2 over here, the number of subshells are 2, which are shown by 2 black boxes, right? So the value of n can vary from 1, 2, 3 up to infinity. This is the principal quantum number. So the electron can occupy any of these shells, and which shell will it occupy is what we're going to learn today. And then we discussed about the azimuthal quantum number, whose value can range from 0 to n minus 1, which notates the number of subshells. And we also said, depending on the value of L, if L is equal to 0, 1, 2, 3, the notations which are given are S, P, D, and F. This is also something that we learned. And then we learned about the magnetic quantum number notated by M, and that corresponds to the number of orbitals present. That notates the orientations as well. Correct? Now, if you let's say that your value of L is equal to P. Sorry, your value of L is equal to 1, that corresponds to the P subshell. Then the M values corresponds to minus L to plus L, whatever the value of L is. And if L is equal to 1, the values of M are minus 1, 0, plus 1. These corresponds to Px, Py, Pz. Okay. We cannot notate whether Px is equal to plus 1, 0, or minus 1. It is not fixed. This is not defined. Okay. Px can take any value. It can be plus 1, it can be 0, it can be minus 1. Okay, so I hope you have got that. And finally, we said that there is the last quantum number, which is a spin quantum number. Each electron has got a spin of plus or minus half. Okay, so this is the summary of what we learned in the previous session. It was all about quantum numbers. And also we did a practice session based on that. The first video, there was a second video on the practice. So the links of those would be given in the description box of this video. Okay, you can refer to that if you want. Now today, we are going to learn about how to write the electronic configuration. What are the rules that governs the electronic configuration is what we are going to see. So let's start. Now understand that electronic configuration is completely a theoretical concept. Okay, it is completely a theoretical concept which is dominated by certain rules, and the first rule that you have to learn is called the off-bow principle. Off-bow principle. Okay. Now, according to the off-bow principle, you can take down the definition if you want. They won't ask you in either of any of the competitive exams, they won't be asking you. But then this is just for your basic understanding. Okay. So according to the off-bow principle, according to the off-bow principle, the filling of electrons in a subshell. So we know that we have a shell which is notated by the red box, and then inside which you can have subshells which is notated by the black boxes, and inside the subshells you have electrons which are being occupied by the orbitals, which are shown by circles. Okay, so these are just random representations. This is not the way a shell, a subshell, or an orbital looks. This is just a cartoon representation. All right. In a subshell, filling of electrons in a subshell takes place in increasing order of energy. In increasing order of energy. Yeah. So the way you can understand it better is the energy of any subshell. So we are talking about subshell, correct? Subshells can be, let's say I take 2p. So what are the quantum numbers that we can derive if a subshell is given? 2 corresponds to the principal quantum number. If it is p, we know that the value of L is equal to 1, right? So 2 quantum numbers are associated with subshell. You can get an idea about N and you can get an idea about L. Correct? So energy is directly proportional to the N plus L values. Okay, so as your N plus L value increases, the energy of that particular subshell also increases. As N plus L value increases, the energy of that particular subshell also increases because they are directly proportional. Okay, now what if you have 2 subshells where the N plus L values are the same? You can note it down. If for 2 subshells, if for any 2 subshells, N plus L values the same, N plus L values are the same, then what we do is the energy is directly proportional to the value of N. Energy is directly proportional to the value of N. Right? Very easy, very, very easy. Let's tabulate a few subshells and you'll get a better idea. Okay, so you can draw a table. Let's say this is subshell, N value, principal quantum number, L value, azimuthal quantum number, N plus L. Okay, let's do one by one. Let's say we start with 1s. Now 1s, what is the principal quantum number? 1. Azimuthal quantum number corresponding to s is 0. I hope by now you know that. L is equal to 0, 1, 2, 3 corresponds to S, P, D, F and so on. Okay. I hope this is known from the previous session. So N plus L value is 1. 1 plus 0, 1. Now let's say I want to compare this with 2s. Principal quantum number corresponding to 2s is 2. S corresponds to L value 0 and N plus L is going to be 2. So it's very clear that as N plus L value increases, your energy also increase. So if I have to compare these two, what I can say is the energy of 2s is greater than the energy of 1s. How did I come to that conclusion? It is from comparing the N plus L value of that particular subshell. Okay? Now, let's add 2p to this. Let's add 2p to this. Now again, principal quantum number is the number of whatever the prefix is. That is the number, right? So this is 2. So 2 and p corresponds to an L value of 1. So 2 plus 1 is 3. Okay, 2 plus 1 is 3. Now I want to compare 2p with 3s, let's say. 2p with 3s is what I want to compare. Now this is the next set. I want to compare 2p and 3s. So for 3s, please write it down on your own. Pause the video and try. So for 3s, n value will be equal to 3. S value corresponds to 0. So n plus L is 3. Okay, so this is the case that I wanted. See? So what happened here? N plus L is the same in both the cases. For 2p also, n plus L is 3. For 3s as well, n plus L is equal to 3. But that doesn't mean that their energies are equal. If you get such scenarios where the n plus L values are the same, you compare the n value. That is what is written over here. So you will compare the n value. So you compare the n value, you see that 2 is less than 3, and hence what you will write is the energy of 2p is less than the energy of 3p. Why? Because 3 is greater than 2. Okay? So here n, the principal quantum number of 2p is less than the principal quantum number of 3s, and hence the energy corresponding to the 2p is less than the energy corresponding to 3s. This was compared only because for these two cases, the n plus L values are the same. Okay, so you got that, I hope so. Okay, let's say I want to compare. Let's frame a question if possible. 4f and 6f. Let's say I want to compare these two. Or we'll go for, yeah, okay, let's see. So please try. N is equal to 4 over here. If it is f, L value is equal to 3. So 4 plus 3 is 7. 4 plus 3 is 7. And in case of 6s, principal quantum number is 6. Azimuthal quantum number is 0. 6 plus 0 is 6. So n plus L values are not the same. If they are not the same, then the way you will write the order is energy of 4f, whose n plus L value is high, will be higher than energy of 6s. Okay? So this is the way you will arrange all the energy of the substrate. So there is a technique by which you can draw as well. I'll be explaining that. Okay? So this is the first rule of Bohr principle. Very easy. Very easy. Now the way you can write down the order, for example, 1s, 2s, 2p, 3s, you cannot keep on calculating the n plus L value. So there is an easy method. So the way you will be doing is, please write it along. 1s, 2s, 3s, 4s, 5s, 6s, and 7s. Because there are 7 rows. Okay, now 1p does not exist, correct? If you have n is equal to 1, the value of L is just 0. L cannot be equal to 1. So 1p does not exist. So 1p won't be there. You will draw the next 2p. Okay, and then you'll write it down, correct? Please write it down. 3p, 4p, 5p, 6p, 7p. Similarly, 2d does not exist. 3d, 4d, 5d, 6d, 7d, 4f, 5f, 6f, 7f. You draw this. Once this is done, to get the order in which you have to fill the electrons in any atom, the way you'll be doing it is, please listen. If you want, you can draw arrows like these. if you want. If it confuses you, okay? So make diagonal strokes. Make diagonal strokes. And then you can connect them. The way you will be connecting them is, see, once you have made diagonal strokes, you can continue. I'm just stopping it over here. Okay. Then what you can do is you connect this head of the arrow with the tail of the next. So this is the head of the arrow where the arrow mark is. And this is the tail. I hope you know that. Okay. This is the head of the arrow and this is the tail of the arrow. What we have to do is we have to connect the head to the tail. Okay. I'm connecting the head to the tail. Head to the tail. Head to the tail. Head to the tail, and so on. You will continue this, right? And then you can easily write the order. Just look at the pattern in which this arrow is moving. For example, it starts with 1s, and then it turns and it comes to 2s. It turns and then it comes to 2p, 3s. So let's write it down. So this is the increasing order of energy, meaning the energy of 1s is the least. And then comes 2s. Then comes, it turns and then it reaches 2p, right? And then it is 3s. And then it turns and then it hits 3p, 4s. After 4s, see, you can see that it is not 3s, 3p, 3d. Instead, it has hit 4s. And now it is turning and then coming to 3D. Very important. 3D. And then next comes 4P, 5S, 4D. I hope you're getting the trend. After 3S, see the way the arrow moves. After 3S, it's going to 3P, 4S. After which it is going to 3D, 4P, 5S. And the next one is 4D, 5P, 6S. So come on. 4D, 5P, 6S. After which again, from 6S, it goes to 4F, 5D, 6P, 7S. 4F, 5D, 6P, 7S, and so on. You can continue it. So this is the easiest way to fill the electrons in the subshells. You need not always write the n plus L value. It will be difficult. Now, once you start practicing this for a while, this will become very easy for you. Okay. Now, the important thing is you use this order of energy when you have a multi-electron system. Very important. Multi-electron means more than one. This order is used when you have a multi-electron system. Multi-electron system. Let's say that your system has only one electron. For monoelectronic system. Mono means one, right? For monoelectronic system, the order is entirely different. You need not draw this pattern. Okay. So if you have a species which has got only one electron in it, then the energy is very easy. 1s is the least. Then comes 2s, whose energy is equal to 2p. Important. Then 3s, 3p, 3d. See, all these subshells which has got a common principal quantum number has got the same energy, which is less than 4s, 4p, 4d, 4f. So if you have only one electron in the system, there are several degenerate orbitals. Very important. What is the term? Degenerate. degenerate orbitals. So these are called degenerate. What is a degeneracy? So there are two orbitals with the same energy, and hence the degeneracy is generally represented by G, that is equal to 2. Here, the degenerate orbitals are 3 in number, so G is equal to 3. Here, G is equal to 4. Okay, so this happens only and only when you have a monoelectronic systems. The moment you have one more electron in the system, the moment you have at least two, what happens? When you have two electrons, electron-electron repulsions come into play. And because of the electron-electron repulsions, the orbitals split. Okay? When you have more than one electron in your system, the orbitals split. And then this is the energy. You have to take the system or the order of a multi-electron system. Okay? So it's very important. Let's say that I have to compare lithium versus lithium 2 plus. Let's say I want to compare this lithium versus lithium 2 plus. Now already I know that the atomic number of lithium is 3 over here, and hence the number of electrons that are present in lithium is equal to 3. But in lithium 2 plus, since 2 electrons are lost from the system, the number of electrons that are present, there's only one electron present, and hence this is a monoatomic species. Sorry, not monoatomic, monoelectronic species. Monoelectronic species. It has got only one electron. So the moment you have got only one electron, the way you will fill the electron is, so you have 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Okay? So I have only one electron. I'll fill the one electron here in the ground state. This is my ground state. Now the second one is my first excited state. And for this first excited state, my degeneracy equal to 2. This is my second excited state, and my degeneracy is equal to 3. For lithium 2 plus, my third excited state has got a degeneracy of 4. This is the case only because there was only one electron present. But what if it was lithium? If it was lithium, then the system what you have is 1s, 2s, 2p, 3s, 3p, 4s, and so on. So you have 3 electrons. So the first to each orbital can accommodate 2. Correct? 1s has got only one orbital. 2s also has got only one orbital. Each orbital can accommodate 2. So the configuration is 1s2, 2s1. 1s2, 2s1. Okay. So this is the way you write the configuration. So you can see that in all these cases, these are all non-degenerate. Non-degenerate orbitals. Non-degenerate means the degeneracy is equal to 1. Please note, it is not equal to 0. This is wrong. Non-degenerate means the degeneracy will be equal to 1. Okay. So this is the first rule that you have to learn, which is about the Aufbau principle. According to the Aufbau principle, the electrons are filled in increasing order of n plus L values. If your n plus L values turns out to be the same, then the energy is filled in accordance with the value of n. All right. And we also saw an exception of if you have only one electron, then the energy, the way you have to fill is something like this. Easy. Okay. Now the next rule is the Hund's rule of maximum multiplicity. Hund's rule. You have already learned these stuffs in your early school days. Hund's rule of maximum multiplicity. Okay. Hund's rule of maximum multiplicity. So what does it say? Take down the definition first, and then we'll do some problems for better understanding. For a given electronic configuration, the lowest energy is the one with maximum multiplicity. We'll explain what multiplicity is. Is the one with maximum multiplicity. Because of which, what you can write is, another definition is if two or more orbitals of equal energy are available, then the electron will occupy then singly first with same spin and then pairing will occur. And then pairing will occur. Singly first with same spin. Important. Okay, I'll explain this. So what does it say? Let's say that you have a configuration like P3. P3 is your configuration, 3 number of electrons, and we know that P has got 3 orbitals, right? P has got 3 orbitals by now, Px, Py, Pz. Now, when you fill the electrons according to the Hund's rule of maximum multiplicity, it always occupies singly first. Singly first means, so now what is the degeneracy of this? 3 orbitals have got same energy. So the degeneracy of all these orbitals can correspond to G is equal to 3 because all of them have got same energy. Correct. Now the way they'll be occupying is 1 in each. 1 in each. This will be the configuration which is the most stable. Most stable means you know that stability and energy are inversely proportional by now. Stability is inversely proportional to energy. So if this configuration is the most stable, then it has got the least energy. It will possess the least energy. Now you might think, why can't it fill like this? It can be singly occupied, but then with different spins. No. This might exist. Okay, I'm not denying the existence of this particular configuration. This might exist, but the energy of this configuration will be high. If energy is high means stability is lower. Okay, so can you understand that whenever you have got some orbitals, first they will singly occupy with same spin, and then only they'll pair up. Okay, then only they'll pair up. Now the thing is, if I want to calculate something called the spin multiplicity, see, multiplicity. What is multiplicity? Multiplicity is simply 2s plus 1. Spin multiplicity is 2s plus 1, where s corresponds to the total spin number. For example, over here, this has got plus half, plus half, plus half. Correct? So the total spin is plus 3 by 2. And the multiplicity, spin multiplicity is 2s plus 1, which is 2 into 3 by 2 plus 1, which is equal to 4. Okay? Which is equal to 4. This is the case. In the next case, where we said that the energy would be high, there, here s is equal to 1 by 2, here s is equal to minus 1 by 2, and here s is equal to minus 1 by 2. Correct? Now you tell me, what is the total spin? Total spin in this case is plus 1 by 2 and minus 1 by 2 will get cancelled, and hence the total spin is minus 1 by 2. Correct? And hence the spin multiplicity. You can take the modulus for the time being, which is 2 into 1 by 2 plus 1, which is 2. Okay, the spin multiplicity is 2. So, according to the Pauli's exclusion principle, the system which has got higher multiplicity will be more stable. Or else, what I can say is stability is directly proportional to spin multiplicity. Okay? Yeah. Now, another reason that is said for, you write down, I'll explain. It's called exchange energy. Exchange energy, a very important term that is needed in coordination. Exchange energy. For example, you have a D5 system, which is like this. And you have another configuration, D5, but then this is like this. So this is configuration 1 and this is configuration 2. So of course, by spin multiplicity, here the total S value will be 5 by 2 and your spin multiplicity will be 6. Here your total S value will be 3 by 2 and your total spin multiplicity will be 4. So the system with higher spin multiplicity will be more stable. This is something that we have learned. Okay. Apart from that, there is something called exchange energy. Exchange energy means, according to the exchange energy, configuration 1 has more number of possible exchanges than 2, which means, let me try to explain. So let's say that this is numbered 1 with an up spin. So this can exchange with this, this, or this electron. Correct? Similarly, if I take this 2, second electron, this can already exchange with 1, which I have already mentioned. Apart from that, this can exchange with the third, fourth, and fifth electron. Similarly, if I check for other electrons as well, there are many exchanges possible because all of them have got the same spin. But in the second case, the number of exchanges are fewer. Why? Why? Because there are only 4 electrons which has got same spin. This one has got a different spin. Correct? The spin of this upside down electron, let's say it is -1/2. It has got nothing to exchange, that is 1 point. Okay? So that electron cannot exchange with anyone. And the other 4 electrons can exchange between each other, but the number of possible exchanges are lower than this one. Correct? And hence, as the number of exchanges increases, as in the case of 1, the stability also increases. As 1 has got more number of possible exchanges than 2, configuration 1 is more stable. A very important thing in the case of coordination. That is why half-filled and fully filled orbitals are more stable. If you want, you can write it down. This is the reason why which half-filled or fully filled orbitals are more stable. Why? Because of high exchange energy. Because of very high exchange energy. Okay? Yes. Coming to the last rule of the day, which is Pauli's exclusion principle. Pauli's exclusion principle. Very easy. You can note it down. No 2 electrons. No 2 electrons can have the same values of all 4 quantum numbers. Very easy. I'll take 2 representative examples and then I'll explain. Okay. Let's say I have 1s. So we know that in 1s, we can have 2 electrons. Now let's say this is my electron 1 and this is my electron 2. What are the 4 quantum numbers? N, L, M, and S. Correct. So I'm numbering them. This is electron 1 and this is electron 2. This is electron 1, this is electron 2. Or if it gets confused with the numbers, let's change. This is electron A and this is electron B. This is electron A and this is B. Now, as both of these electrons are present in 2s, as both of these electrons are present in 1s, the principal quantum number 1. They are the same. What would be the azimuthal quantum number? Again, as they are occupying the s orbital, 0. M value again, 0, but S value. One has got a positive spin, other one has got a negative spin. So can you see? N is same, L is same, M is same, but S is not the same. It means maximum 3 quantum numbers can be the same, but all the 4 quantum numbers will never be the same. all four quantum numbers cannot be the same. If you take any two electrons, they cannot have same quantum numbers. Okay, let's take the case of lithium. If I want to take the case of lithium, it has got one S, two electrons in one S, two electrons in one S, and one electron in 2p. Correct? Now I'm naming these electrons as A, B, and C. So I have A, B, and C. And again, I want to list the N, L, M, S values. I want to check whether any two electrons in a system can have same set of quantum numbers. So let's talk about A. It is present in 1s. So the value of N will be equal to 1. L value will be 0. M will of course be 0. And S can be plus 1 by 2. Let's say because it is upright. In the case of B, which is there in the same subshell, 1, 0, 0, minus 1 by 2 because it has got an upside down spin. Now C, that is present in a different subshell. So the value of N now is 2. L is 0, M is 0, S is 1 by 2. Now can you see the difference in the quantum numbers between A and C? Correct? This time, if you compare A and C, S is the same, M is the same, L is also the same, but N, there is a difference. So I hope you have understood now that if you take any two electrons within a system, any two electrons within one system, any two, it need not be within the same subshell, any two within the same system, they won't be having all the four quantum numbers with the same set of values. Okay, there will be a difference, and hence we come to an end of this particular session. In the next video, we'll be doing many problems on the basis of whatever was discussed. We'll again, practice some examples on how to write the electronic configurations of atomic numbers that are greater than 30, 40, 50, etc. We'll practice some problems as well. We'll discuss some exceptions. So we'll see in the next video. Bye.